Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 74, and it is entitled Single-Slit Diffraction, Diffraction Gratings, and the Thin Film Interference. Your authors have chosen to combine three topics dealing with wave optics together in a single lesson. The task is a formidable one, and the topics are not as likely to appear on the AP exam as, say, Faraday's law of electromagnetic induction. We'll take the topics one at a time, and we'll cover them only in a cursory way, leaving out much of the theory and just writing down the main equations without proof. Let's begin with single-slit diffraction. Diffraction may be defined as the bending or spreading of a wave around some barrier that's placed in the wave's path. Cast your mind back to 1803, if you will. Thomas Young demonstrated double-slit interference using a geometrical argument that we followed in Lesson 57. That led to what we call the Young's double-slit equation, d sine theta is equal to m lambda, where d represents the slit separation, lambda is the wavelength of the light that's used, m is the order number representing the bright fringes if they're integers and dark fringes if they're half integers, and theta is the angle between the central maximum and the mth bright fringe as seen from the slits. Young's work demonstrated conclusively for the first time that light behaved as a wave, and with his experiment he was able to measure the wavelength of light for the first time. Young's work was reproduced and extended by the Frenchman Augustin Fresnel, a man you may never have heard of, but whose work you benefit from every time you go into a theater. Most theatrical lights employ a special piece of optics called a Fresnel lens, which Fresnel first developed for use in lighthouses. The Fresnel lens is cut in a special way so that a smaller piece of glass is needed than is required by a convex lens to produce the same magnifying effect. In 1818, Fresnel entered a special competition sponsored by the French Academy of Sciences, presenting a paper entitled Memoir on the Diffraction of Light. His theory represented light as a wave, as opposed to a bombardment of hard little particles, which was the subject of a debate that had lasted since Newton's day. The judging committee included Pierre Laplace, Jean B. Biot, Simeon Poisson, Dominique Arago, and Joseph Gay-Lussac. A formidable group indeed. You may never heard these names, but these are all important French scientists from the early 1800s. Poisson, a member of the judging committee for the competition and a severe critic of the wave theory of light, used Fresnel's theory to deduce a seemingly absurd prediction that a bright spot should appear behind a circular obstruction, a prediction he felt was the last nail in the coffin of Fresnel's theory. However, Dominique Arago almost immediately verified the spot experimentally, and that's what's seen in this figure here. Fresnel won the competition, and although it may be more appropriate to call it the spot of Arago, this spot goes down in history with the name Poisson's bright spot, like a curse. This is an image of Poisson's spot, and if you're fortunate, you'll have an opportunity to see this in a class sometime. It's not hard to produce using a laser and a small ball bearing. Your authors illustrate the diffraction pattern produced by a single slit, and the important equation is this: d times the sine of theta is equal to n times lambda. But there are some very important differences between this and the equation that looks much like Young's double-slit equation. In this equation, capital D is the width of the slit, and n represents the orders of the dark fringes. In single-slit diffraction, there is a double-wide central maximum, and then dark fringes receive the integers, with bright fringes occurring at the half integers for n. There is a similar small angle approximation that can be made for single-slit diffraction as is done for the Young's double-slit. The diagram that you see here from an online version of Encyclopedia Britannica exhibits some of the geometry. The slit width, indicated in red here, is equal to d. This central maximum right here is wider than the central maximum that occurs for Young's double slit, and then we have n is equal to 1 corresponding to the dark fringes, and then you count up, n is equal to 2 for each of the other dark fringes, as opposed to m, as in Mike, equals to 1, 2, 3, and 4 for the bright fringes in Young's double slit. Let's solve a numerical example. 74.1. Light from a monochromatic source has a wavelength of 750 nanometers. The rays pass through a slit 1 times 10 to the minus 2 millimeters wide, and the diffraction pattern is illuminated on a screen 1.0 meter away. A. What is the angle between the center of the first minimum and the center of the central maximum? And B. Approximate the distance y between the center of the central maximum and the center of the second minimum. Let's look at the geometry of this first and then solve this problem. Remember, we'll have to all work in the same units, so I'm going to convert nanometers and millimeters into meters. I'm looking for the angle theta, and I start with the single-slit diffraction formula. I'm going to solve that equation for theta. Now I'll substitute the numbers and figure out what theta is. I find that the angle is 4.30 degrees. In part B, we want to approximate the distance y between the center of the central maximum and the center of the second minimum. Let me sketch that. I've gone to the other side and I'm measuring this distance y between the center of the central maximum and the second order dark fringe. N is equal to 2. Again, I can write the single-slit diffraction equation. The small angle approximation allows me to say that the tangent of theta, which is the sine of the angle divided by the cosine of the angle, and these are all theta 2, that's almost equal to the sine of the angle, because cosine is almost equal to 1 when theta is small. So I want to make the approximation that d times the tangent of theta 2 is equal to n lambda, and since the tangent is equal to y over L, then I can say d times y over L is equal to n times lambda, again for small theta. With that said, let's solve that equation for y, and let's make our substitutions. And now I'll substitute those numbers into my calculator, and I get the second minimum occurs at y is equal to 0.15 meters, which is 15 centimeters. Now I'll make a note here, and I'll see that I have misread the way that the authors have written in the textbook, and what they have written is actually that it's the second maximum that we want. So I'm going to go back and solve this again. Everything is okay, but now I want to use the fact that n is equal to 2.5, because the second maximum occurs right here where n is going to be between 2 and 3. So let me make the substitution n is equal to 2.5 and solve the problem again. And now let me substitute those numbers into my calculator, and I get that the second order maximum is going to occur at about 19 centimeters, just under. Now let's move on to the diffraction grating. A diffraction grating can be thought of as a picket fence for light, consisting of closely spaced ridges or rulings that diffract light that encounters them. This diagram shows an image of a diffraction grating in schematic form. Common in many classrooms, transmission diffraction gratings are frequently mounted on cardboard squares, much like slide transparencies, making the diffraction grating easily used by students to observe light spectra. Whereas reflection diffraction gratings are commonly found in spectrometers used in scientific research. You see diffraction phenomenon every time you look at dispersed light that's reflected from the back of a compact disc. The closely spaced grooves on the back of the disc act as a diffraction grating. It turns out that the equation governing the diffraction grating's operation is identical to the Young's double slit equation, which is little d sine theta is equal to m, as in Mike, times lambda. The variables in the equation for the diffraction grating have the same meanings as the variables in Young's double slit. A big difference, though, is that diffraction gratings have much smaller slit separations than you'll normally find in Young double slit, and generally you cannot use small angle approximations for them. In addition, most diffraction gratings are usually characterized by something called the grating constant, or the line spacing. This will tell you the number of lines per centimeter, or the number of lines per inch, that are ruled into the surface of the diffraction grating. This line spacing is how you'll get information about the slit width, little d, and so you'll use the line spacing or the grating constant to figure that out. Let's look at numerical example 74.2. A diffraction grating contains 10,000 lines per centimeter. Calculate the first order angle for light of wavelength 700 nanometers. In this problem, this 10,000 lines per centimeter is what we would refer to as the grating constant. If there are 10,000 lines per centimeter, then what that means is the reciprocal of that number is the number of centimeters per 10,000 lines. 1 centimeter is occupied by 10,000 lines. So the spacing between two adjacent lines is going to be 1 centimeter divided by 10,000. In other words, D is 1 centimeter divided by 10,000. That's going to be the reciprocal of the grating constant. In this problem, we're using white light that has a wavelength of 700 nanometers, and we're trying to find the first order angle. So what is theta equal to? And we're going to see that theta turns out to be a number that is not a small angle. So we could not use the small angle approximation in this problem. Let's write down the grating equation, and let's solve that equation for the angle. And now let's substitute the numbers. And again, I'm going to have to work in a consistent set of units, so I'm going to convert centimeters into meters. And now put in the numbers and figure out what the angle is. I get that the angle is not quite 45 degrees. This is not a small angle, so I cannot use small angle approximations.